We've already seen that a mobile robot, when moving, uses two types of information. Information about its own movement, odometry, and information about external references, localization. A mobile robot can even detect obstacles using its sensors, maybe distance sensors, for example. But if we want to help the robot to do tasks such as planning paths or trajectories, or helping even to detect fixed obstacles, the robot will benefit from what we call a map. And that gives rise to the third type of information, maps. A map in robotics is not that different from what we call a map, the map a tourist might use when visiting an unknown city. The map somehow charts the environment, its shape, its limits, and the position of fixed obstacles. In the case of static and very well-known environments, we could maybe provide the robot with map in advance. That would happen in some industrial environments. But in other type of environments where we don't know that environment very well, or even that is a dynamic environment, it's the robot itself who must build the map. Think, for example, in the case of vacuum cleaner robots. Of course, the manufacturer of the robot does not know the map of the houses. Doesn't know. It doesn't know. I shouldn't know. So it's the robot itself who builds the map, and the robot builds the map using information provided by its own sensors. Information which we could consider localization information. So say that localization and mapping are very intertwined tasks. And in fact, the algorithms that the robot use are of the type called SLAM, simultaneous localization and mapping algorithms. There are two types of maps. For very simple environments, we could use continuous maps. In continuous maps, we usually represent obstacles via the coordinates of its vertices. But in other cases, and in the most common cases, we use static maps or grid maps. In grid maps, we divide the space into cells, and we just mark if the cell is occupied or not. If the cell is not occupied, it's free space. And if it is occupied, that's an obstacle. But as the information from the sensor is not very accurate, we usually assign not just if the cell is occupied or not, but the probability of being occupied. A high probability tells that probably there is an obstacle there, and a low probability says that probably that's free space. There are algorithms such as frontier algorithms that get the information via simple exploration. But usually the results of the algorithm is better if it also uses some context knowledge. For example, if a vacuum cleaner robot is moving in a house, it can know that the angle between walls is 90 degrees. They are the orthogonal. And the robot uses that information to build a better map, although not using a very precise information. And so with maps, we've completed the information the robot moves, information about its own movement, odometry, information about external references, localization, and general information about the environment and the obstacle maps.